Hi everybody, this video is a summary of the video Optical Mineralogy Big Picture. And I just wanted to make this video to go over some important concepts in optical mineralogy without getting bogged down in the detail that we go through in our other video. But what I will do is add links in this video to that full-length video in case you want to delve deeper into a particular concept. So let's get to it now and take a look at what a mineral is. There are 5 main characteristics which define a mineral, some of which are a bit squishier than others, but for our purposes, the definition we'll use is that a mineral is a naturally occurring, inorganic, solid, that has a definite chemical composition and an orderly internal arrangement of atoms. And really, the pieces of this definition that are going to matter a lot to us today as we go forward are that definite chemical composition and the orderly internal arrangement of atoms in a mineral, which gives a mineral structure. So with the definition of a mineral fresh in our mind, let's go and look at some of the larger concepts that we've talked about before in our other videos. So this triangle of concepts may be familiar to you, but now that we've thought about the definition of a mineral, let's add a bit more to it. So, all of these concepts are going to be derived from the chemistry and the structure of a mineral. And the simplest way to sort of think about this is probably to do an example. So, as you've probably guessed, given my love of corundum, today we're going to talk some more about corundum. So when I say corundum, what I'm actually saying is the mineral with the chemistry aluminum oxide, Al2O3, and with the structure of having oxygen in a hexagonally closest packed arrangement, and then having aluminum occupy 2/3 of the octahedral interstices between those oxygen atoms in the hexagonally closest packed arrangement. Because the bonding in the corundum structure is predominantly ionic, we can also make a fairly simple model of the corundum structure using marbles and ball bearings. The larger clear marbles will represent oxygen anions, and the smaller metallic ball bearings will represent aluminum cations. So let's take a look at this structure model. So here's the first layer in our structure. We'll call this layer A1, A referring to the hexagonal close-packed oxygen, and 1 referring to the pattern in our aluminum ions. Next up then would be layer B2. Our oxygen will then repeat, but our aluminum will not, so we end up with A3. And now our aluminum finally repeats, but our oxygen will not, so now we're to B1. Hopefully you haven't turned off the video and run away yet, because next up we have exciting A2. And at the end, we finally have our last unique layer of B3. Adding an additional layer after this would bring us all the way back to A1. So we've now built a tiny corundum crystal. Hooray! And now for the part of the story where I'm in a bit over my head, because we're going to talk about space groups. And so what we're going to delve into now is the symmetry represented in our corundum structure at this scale. If we imagine our structure infinitely repeating in all directions through space. So the space group of corundum is R, 3 bar, 2 over C. Sometimes this is shortened to R 3 bar C, but they mean the same thing. Here's a 2-dimensional representation of the symmetry elements in our 3-dimensional structure. For a deeper dive into all of this, you should check out the website in the lower left corner of this figure. There you can go through all 230 space groups in gory detail. So what is the space group R 3 bar 2 over C? This is one of 230 possible ways in order to build structures that repeat in 3-dimensional space. And in order to have these structures repeat in 3-dimensional space, there's going to be symmetry elements in particular directions through our structure. We'll leave more detailed identification of these symmetry elements to the other video, but for now note that there are repeating patterns in this structure, and these are related to one another by these symmetry elements. And if we rotate our structure by 90 degrees, we can see the geometric relationship between these different symmetry elements. Going back to our original view, we have one more important symmetry element to add on here. Our space group contains more individual symmetry elements that we're not going to take the time to identify, but here's an overlay onto our corundum crystal structure if you'd like to dig deeper. So let's go back to our triangle of big picture concepts. We've covered the chemistry and structure that define corundum, but now let's take a look at the crystallography of a macroscopic corundum crystal. So let's head to the lower left portion of our triangle of concepts. Here we have a fairly euhedral macroscopic corundum crystal. And when we think about symmetry on the macro scale, what we're going to think about is point group symmetry and not the space group symmetry that we were talking about earlier. So there are 32 point groups, and let's take a look at the point group symbol for corundum. The point group symbol for corundum is 3 bar 2 over m. Wait a second, that sounds suspiciously similar to our space group symbol of r 3 bar 2 over c, doesn't it? And it is. All of our 230 space groups can be grouped under our 32 point groups. When looking at this macroscopic crystal, we can identify symmetry elements associated with our point group. We'll leave the details again to the other longer video. In this direction, what we're actually seeing is the threefold rotoinversion axis of our corundum, and this is our C crystallographic axis. So we are looking down the C axis in this view. Our A axes will then lie in a perpendicular plane, and these will be twofold rotational axes, and then perpendicular to our A axes will be mirror planes. So let's rotate the crystal 90 degrees now, and we can take a look at the crystal viewing along one of our A crystallographic axes. So, back to the big picture. We've got our corundum structure and space group symmetry going on at the micro scale. We've got our macro scale corundum crystallography and point group symmetry. And it should be apparent at this point that our macro scale crystallography and point group symmetry are dependent upon what's going on at the micro scale. So let's do the same exercise, taking a look down one of the A axes of our crystal. So we're looking at the micro scale. Here's the same view at the macro scale with our crystal. And then here's those two views side by side. So while it's delightfully nerdy to look at how the microscopic structure of corundum influences the morphology of macroscopic crystals of corundum, it's a bit more important than just that. We can actually use this to our advantage, because the microscopic structure of corundum is going to control a whole bunch of different physical properties that vary with direction in the mineral. And not only physical properties, but chemical properties too. So properties that vary with direction in our crystal can include things like hardness, thermal conductivity, electrical conductivity, our optical properties, which is what we're going to focus on here, rates of various chemical reactions, and cleavage in addition to others. So going back to our triangle of big picture concepts, if we know that we have the mineral corundum, and we have a nice macroscopic crystal where we can identify the crystallography, I can tell you the optical properties that we'll see based on that knowledge. But the bigger picture here is that because of how all of these concepts are related to one another, if we can figure out any two pieces of this triangle, we're usually able to figure out the third as well. So now that we've talked about the microscale structure and chemistry of corundum, along with the macroscopic crystallography of corundum, let's now turn to the optical properties. And our macro-scale natural corundum crystal isn't going to cut it for optical properties. As you can see here, it's very much not transparent. And if it were, it would have been quite expensive. But luckily, there's a large amount of synthetic corundum on the market in various forms. I'm going to use some flame fusion synthetic corundum in order to investigate our optical properties. So this flame fusion synthetic corundum has been cut very specifically to highlight these optical properties, and we are currently viewing this sample with plain polarized light that is vibrating in a north-south direction. And if you want a bit more depth as to what we're doing here, you can check out Optical Mineralogy Uniaxial Minerals video, or Optical Mineralogy Improved Uniaxial Optic Axis Interference Figure video. But basically what we see here as we rotate our sample in plain polarized light is not really much of anything. So we're not seeing any pleochroism in this direction. The pleochroism would be observable as a change in color as we rotated the crystal here. For this particular color of synthetic corundum, the lack of pleochroism is actually telling us the direction we are viewing through our crystal. But more on that later. So now let's choose a new viewing direction through our synthetic corundum crystal. So I'm actually going to take a moment and line everything up, appropriate for the flip that we want to do, and you'll see in a minute why I have to take this other additional little 90-degree rotation. So what we're going to do here is basically pick up the crystal and rotate it 90 degrees. And we can immediately see something interesting going on here. The color looks rather different in this direction. Let's now rotate our crystal with our new viewing direction and see if anything interesting happens. So as the crystal spins, we go from sort of a lighter raspberry color to a darker purple. That looked very similar to the original dark purple we started out with the other viewing direction. So what's this difference in optical properties with viewing direction caused by? If you guessed the microscopic structure of corundum, you are correct! So while these two videos aren't perfectly synchronized, take a moment and think about what is being illustrated as we rotate both our synthetic corundum sample and our microscopic corundum crystal structure. This direction through our crystal is where we have a threefold rotoinversion axis. And this symmetry element is actually responsible for the optical properties that we end up seeing in this crystallographic direction. Pleochroism as a phenomena occurs when there's differential absorption of different wavelengths of light as you travel through a crystal. But the threefold rotational symmetry of our crystal structure, coupled with the nature of light, prevents any differential absorption of light as it travels through our crystal in this direction, no matter how we rotate this crystal in this plane. It also means that light traveling through our crystal in this direction is only subject to one refractive index, and that refractive index is known as omega. We know that our A crystallographic axes lie in a plane perpendicular to the C crystallographic axis. So reorienting our flame fusion synthetic corundum by 90 degrees along with our microscopic corundum structure model yields the following results. We note a change in color with the reorientation of our synthetic corundum sample, and this change in color is a result of our plane polarized light interacting with a different direction through our corundum crystal structure. This change in color is associated with a different refractive index as light travels through this direction of our crystal, known as epsilon. Spinning the corundum sample here yields pleochroism as we return back to the darker purple color associated with refractive index omega. So I hope this demonstration has helped you understand how the microscopic crystal structure of corundum actually leads to the optical properties that we see at the macro scale. A three-dimensional representation of the different refractive indices caused by our microscopic crystalline structure is known as an optical indicatrix. Here's a representation of the optical indicatrix for corundum. This is highlighting the two different views through our optical indicatrix that are equivalent to the views we've taken through our flame fusion synthetic corundum. And once again, our optical properties and our optical indicatrix are a result of the corundum crystal structure. Looking down the c-axis of our crystal, that means that we can only see refractive index omega in this particular plane, and so we're not going to be able to see any fun pleochroism in this direction. Looking down anywhere in the plane of the A-axis of our crystal? Well, we'll be able to transition between refractive index omega and refractive index epsilon, depending on how we rotate our crystal in this particular plane, and so we can see fun effects like pleochroism. So the big picture of the big picture video is that we can tie together all of these different concepts because of the chemistry and structure of our mineral. And that's what we did today in depth for the mineral corundum. Corundum as a mineral is defined by its chemistry and structure. These in turn determine the macroscopic crystallography that we can see in euhedral crystals. And the chemistry and structure also determines various physical and chemical properties that vary with direction in our crystal. Our focus is on how the optical properties vary, but we could have chosen others as well. Understanding the relationships between these concepts allows us to either identify unknown substances or to orient substances appropriately to take advantage of specific physical and chemical properties that vary with direction. Many high-tech applications require this type of knowledge, from developing quartz oscillators for wristwatches to developing monocrystalline silicon wafers appropriately oriented for the production of computer chips. Our modern world depends on crystalline materials and the anisotropy they display. So, thanks again for watching, and have a great day.